Alright, so this is Fluent Flow Assignment 1, and these are values for the project. We're doing a height of 3 millimeters. So we're going to go ahead and open Workbench. And then we're going to do Fluid Flow with Fluent. And this is case 1, so we're going to do the Poiseuille flow. So we're going to go and right click geometry and do design modeler geometry. Once that's open, we go and we click the z-axis to, just see the XY plane. We add a rectangle under sketching. And then we need to define our units, which is in millimeters, and then specify our dimensions. So the horizontal is going to be the length, which is 450 millimeters, and our height, or like the diameter of the pipe is just 3 millimeters. So in modeling, we can go down to our sketch and press concept, and we're gonna add some filling to the sketch that we just did and apply that. So if we zoom in, you should see that the the figure is filled with gray, and that's once we press generate. And after that, we can go ahead and close out the app. So let's press mesh. So let's fix our z-axis, and we're gonna go ahead and go into edge select mode and start naming all sides by pressing N. And we're gonna name the top one the top wall, and press OK. And then we're gonna name the inlet. Then we have the outlet. It's a little hard to select, so let's name the bottom panel the bottom wall. And then here we have our outlet. So you can see here our name selections, and then we're gonna generate. And then we're gonna insert, like after we select all sides of our mesh, we can insert a refinement, and that's just so that we have more resolutions, for when we do our simulations, so our results are more accurate. We press generate again after we move the refinement up to 3, and then we can add even more resolution by changing the element size to 0.001. And you can ignore that, and just verifying that it's set. And after the bar turns black like that, then we can exit out and go to our setup. Oh wait, let's update the mesh and then do our setup. So we're going to do double precision to make things more accurate. And for our solver processes, let's just check how many we have by going to Task Manager. And we want to do one less than our logical processors. So we have 20, so we're going to do 19. And then we can start. So we're gonna go into models and make sure our viscous is laminar, because that's one of the requirements of this project. Make sure everything else is off, and then go into our materials, and I'm just gonna change our viscosity to 1.8 just to simplify the math a little bit. I'm gonna leave the density, but whenever I calculated my Reynolds number, I used 1.8, so we're gonna go with that. And for our boundary conditions, our inlet for Poiseuille, it's just, the pressure or a velocity inlet, and I think that's gonna be 5 meters per second. And our outlet, we want to make sure that we prevent reverse flow. Apply that. And our wall, our bottom wall, or we want both walls to be stationary, so let's just verify that. And then we're going to go to our reference values to verify that all the information is correct. First, let's go to our residuals and change that to 10 to the power of -6 or 1. It's going to be 1e -6. And then we see our viscosity didn't update, so let's change that really quick. And the rest, these are our values. I'm gonna leave the velocity because I think we set it in our inlet. Yes, that's showing 5, so everything's good to go for our initialization process. And we're gonna set the number of iterations to 20, and we'll see that whenever we do our calculations. We just want it to reach, or to have less error. That's why we're doing 20. So after we initialize, which may take some time, it'll indicate that it's done, and then we're good to go run the calculation. And we want to do 1,010 iterations again, just to get really precise values. And you can see the scaled residuals, it decreases as the number of iterations increase. and we can scroll up at the bottom, and we can see that our solution converged before we reached 1010 iterations. So that's good, and we can exit that and go ahead and see our results. So let's add a contour, and this is gonna be symmetry 1. We're dealing with velocity, and our number of contours is going to be 100. Because this first run I made a mistake for the other one, so you'll have to keep an eye out on the inline and midlines. Just make sure that the number of resolution is always 100. So we're gonna fix our legend to make things neater. And change it to horizontal. And under our parents, let's do fix and apply that. So now it's up there, and we can add our velocity vectors. It's the same as the contours with symmetry 1 and velocity. And we're also going to reduce the size. Oh, the contour might be blocking it, so you just have to hide it to see your velocity vectors. We're gonna reduce the size of our vectors just to make things neat. And that should be good. So you can see, it's blue towards the walls, and right towards the center, so that's where the greatest velocity is, and that's where it should be because it's only an inlet. So let's add a line, and this is going to be our midline. So half of 450 is 225, and that's going to be the same case for our second point. And we're going to change that to 0.01 to make it an appropriate size. So that's our midline. We're going to add another one for the inline, and in this recording I don't show this, but we also did one for the developing flow, which was just like a little bit less than halfway to the midline, or I wouldn't say that, I'd say like 1/5 of the way to the midline is where the developing flow kind of stops. So we can see the velocity vectors of our inline, which looks good, what we expect, and this is the developing flow. So we can go to our chart viewer and add a chart for case 1. We're going to name it our velocity profiles. Our x-axis is velocity again, and our y axis is just going to be y. So in our data series, we're going to do our midline, and then our location is going to be that first line that we made. And it looks a little bizarre right now, and that's only because we didn't add enough resolution to our inline and middle line. So we'll go back and add that so that it can, look as we expected. So down there we have 100 samples for all of them. And once we do that, it should look like a parabola, and it should be centered, in the middle. And we can see that our inline and our midline are overlapping. And once we add our developing flow, we'll see that it doesn't match up exactly. And that's what we expect because, the flow, it hasn't reached its fullest velocity. At the center. So that looks good, and let's export that and move on to case 2. So after we duplicate our project, we can go ahead and rename it to our co-wet flow for case 2. And case 2 is just going to be case B is going to be the top wall moving. And we can go into our same setup with the same settings. And then just verify that our viscous is still laminar. And for our boundary conditions, we have to change the inlet to a pressure inlet so that we don't have any velocity and prevent reverse flow. Our outlet should look the exact same. And then the bottom wall should stay the same as stationary. But our top wall is going to be that moving wall with the velocity of 2, and we have the no slip condition, so we can apply that and close, and then just verifying. And our reference values should all be the same. Our residuals should have the same settings that we applied before. And our initialization should look the same as well with that 20. So we're good to initialize. And run our calculation. So we can see that our solution converged before the 1010, and that our residuals, our error is decreasing. So we can close that and open our results panel. So we have the visualization of our flow, which looks good with the blue at the bottom and the red at the top with our velocity. And even with our vectors, we can see that the top wall is moving and it has the greatest velocity. So we know that the values, match our flow visualization. So we can go ahead and start our chart. And we're going to input the same settings as last time. The only thing that's really different is the graph, which should show a linear relationship with the velocity and the height, because we know that our max height is going to be, or our max velocity is going to be at the max height, which is where the wall is moving. So even with our developing region, it will waver a little bit, but it will also indicate that it has that same linear relationship. And after exporting that, we can move on to case C, which is our hybrid flow. That's going to have the inlet velocity and the top moving plate. So let's rename that and open our setup, which is the same, and it's going to be the same process of just verifying that our material, or our our viscous is still laminar, and our boundary condition, we're going to change that back to the velocity inlet and make our velocity, I think it was 5. And then just to verify, our outlet is going to be the same to prevent reverse flow, and we're only going to change our top wall again, or just leave it the same, to be honest, and apply that. Our bottom should still be stationary. Our reference values are the same, and we can initialize. So our solution converged, and we can look at our scaled residuals and see that they're decreasing. So we can go ahead and exit out of the app and take a look at our results. So the main thing that we're looking at for this case, or looking out for, is that the bottom wall is stationary, and we can see that better, towards the midline. But the bottom wall is stationary, the top wall has little velocity, and the center has greatest. And this is also mirrored in our graph, where we see that our velocity starts at 3 at the height of, or our velocity is 2 at the height of 3, and is greatest towards the center. So that's the end of the ANSYS project. Thank you.